Hi, my name is Hongji Kim from Center for Neuroscience Imaging Research and Sungkyungan University in South Korea. This is a presentation that I will give at 2023 OHBM, and the title is Introspection Enhances the Accuracy of Functional Connectome Fingerprinting and Trait Prediction. I believe that everyone would agree that every person or brain is heterogeneous. And this individual difference comes from affective meaning, which we believe that every person has in their mind. And this has multiple components, such as past experience, how you think about yourself, your personal beliefs or valuation, social context, current situations, bodily response, affect that you currently have, and also introspection and prospection. Because these affective meaning is different for everyone, even though there is a same event or stimuli, the responses will be different for everyone. So everyone will respond in different emotions, behaviors, and decisions. Where does this individual difference come from? Brain structure, function, and intrinsic organization like functional connectivity are different for everyone. And predicting individual differences from brain measures can be one of the most important steps toward individualized neuroscience. In 2015, there was a paper that showed that functional connectivity can serve as a fingerprint to identify each individual from a large group of people. They showed that brain activity can work like a fingerprint, which is unique for everyone, so everyone has their own signature pattern. And also, functional connectivity is known to be predictive of individual differences in behaviors and traits, such as their ability of attention, working memory, and so on. And recent studies also have shown that functional connectivity measured during traditional and naturalistic tasks can be better than those measured at traditional resting state for both fingerprinting and behavior prediction. There has been a recent recommendation that we should put rest to rest and find a better paradigm that can replace traditional resting state. And assessing participants' mental content during an fMRI scan can be challenging because we have to rely on their posteriori introspective evaluation. We can assess our thinking or we can introspect and report accurately about our introspections. And there has been two non-retrospective methods that has been used. One is think aloud method and one is descriptive experience sampling method. In this study, we used a task with combination of these two methods, and we aimed to investigate that if we use introspective thinking through intermittent thought probes, can we improve functional connectivity-based fingerprinting and also behavior prediction beyond pure resting scans? So our research questions can be addressed in 3 questions. First, if we add intermittent thought sampling during resting state fMRI, will we have better functional connectivity-based fingerprinting? Second, if so, what are spatial and temporal features of those sampling that contribute to better fingerprinting? And lastly, can those sampling also improve the prediction of personal trait? So let me start with the first research question. If we add intermittent thought sampling, does it improve functional connectivity-based fingerprinting? So our overall experimental paradigm looks like this. Participants answered multiple behavior batteries, and then they went through fMRI scan, total of 6 runs. And during the scan, there were 2 runs of resting state, where participants were asked to look at the fixation point for 14 minutes and do nothing. In those sampling runs, the participants were asked to look at the fixation point for about 1 minute, And whenever the instruction saying, "What are you thinking right now?" pops up in the display, they had to speak out one or two words that can represent their current thinking at the moment. And they repeated this for 15 trials for each run, and we had a total of 61 healthy participants in this data set. To perform connectivity-based fingerprinting, we first had connectivity metrics for each run with 265 nodes leading to about 34,000 edges, and each run for each participants were made into connectomes. And we compared the correlations between two runs for same subject or different subject. For example, we compared subject 1's run 1 and all the other subjects run 4. So we compared subject 1's run 1 connectivity with all other participants' run 4 connectivity, and if his or her own connectivity pairs has the highest correlation, we saw it as success. And we calculated the number of participants with successful identification out of total number of participants as the identification rate. So when we compared the resting states and thought sampling runs, we got this ID rate. So you can see that in this box, which was done between thought sampling runs, shown as orange color here, they showed a higher identification rate than when we used resting states, or when we used resting state and thought sampling runs. So fingerprinting accuracy or identification rate was significantly higher in thought sampling runs compared to rest-only scan. And we wanted to see why are these identifications so higher in thought sampling runs compared to resting state runs. So we looked at within subject correlations and between subject correlations, and in thought sampling runs, we could see that in every subject, within subject correlation is always higher than between subject correlation. However, when we used resting state, in some participants that's marked in blue lines, they had higher between subject correlation than within subject correlation. That led to failure in self-identification. And also, we asked the participants to come back after 3 months and do the same session again. And the fingerprinting result was same across sessions as well. Even between sessions or even 3 months later, when we used those sampling runs, it gave us better information of individual unique patterns than resting state. So to answer the first research question, we can say that fingerprinting accuracy is significantly higher in thought sampling runs than resting runs. And this effect was consistent in the retest session after 3 months as well. So moving on to our second question, what are spatial and temporal features of thought sampling that contribute to better fingerprinting? So this figure shows the spatial features. So here it shows the top 0.05% edges with highest differential power, which was defined as important edges contributing to the fingerprinting. And you can see that important edges are mostly distributed among high-order networks like DMN or attention networks and frontoparietal networks. And when we tried to do the fingerprinting with only small number of edges, like 5 edges, 25 edges, 50 edges, when we used edges with top differential power, we could reach like around 100% when only using about 50 edges. So it shows that very small number of edges actually contribute to the successful identification, and those edges are distributed in high-order networks. And when we saw the temporal features, we didn't find any significant effect from temporal features. And when we saw the spatial temporal features, looking at the how those networks contribute during each sliding window time, we found out that important networks like dorsal attention, ventral attention, frontoparietal, and DMN, they contributed to the successful identification throughout the trial. So, to sum up, higher order networks play more important roles in connectome-based fingerprinting, and temporal features were not significantly important. And those important networks were consistently important throughout the trials. And the last question, can thought sampling improve the prediction of personal trait as well? We used connectome-based predictive modeling to see if those sampling runs can give better prediction for trait as well. And this CPM is basically using linear model to predict behavior scores based on the brain connectivity. So we had multiple behavior batteries like depression, anxiety, and other mental health related questionnaires. And with factor analysis, we ended up with general affective factors. And this shows 5 top factors, which I will not go detail because of the time issue, but the first factor was about negative affectivity, second was about anxiety and rumination, third, imagination, fourth, positive affectivity, and last, mindfulness and emotion regulation. As a result, you can see that in all 5 factors, the thought sampling runs, shown as orange color, shows higher performance than resting runs, shown in green color. This shows that for connectivity-based predictive modeling, data collected during the thought sampling scan predicted individual differences in traits measured with multiple behavior surveys significantly better than when we used rest-only data. So to answer the last research question, we can say that adding intermittent thought probes to resting scans can produce more accurate functional connectivity-based predictions of trait-like features compared to pure rest. So to sum up, the take-home message of this presentation was that adding intermittent thought probes to rest scans to enhance introspection can give us better functional connectivity-based predictions of self-identity and trait-like features compared to pure rest. It's because thought sampling provokes metacognitive or introspective process, and these findings provide a possibility of using thought sampling not only in healthy populations, but also in clinical populations, given that it is a simple but potent method for capturing individually distinct functional connectivity features. Future analysis will probe on what features, like the contents or frequency of sample thoughts, drive this enhancement of the individual signal. This is the reference list that I used in this presentation. And I'd like to thank Chung-Wan Woo and Emily Finn, who are the corresponding authors of this project. If you have any questions, please don't hesitate to reach out to me. Thank you for listening. Bye.